Hello, everyone. My name is Anirban. I'm a postdoc at SLAC here. To start with, I want to thank the organizers for arranging this nice workshop and for giving me this opportunity to present my work here. Today, I'm going to tell you about neutrino self-interaction as a solution to the Hubble tension. I say solution to the Hubble tension, but as we go along, we'll see how much it actually can solve or not solve this tension. So this talk will be based on this paper here, which I wrote with my friend Shubhajit Ghosh. Here's a brief outline of my talk. I'll start with telling you about a brief primer on the cosmology of self-interacting neutrino. Then I'll explain what are the new things that happen in this cosmology in case of flavor universal flavor universal neutrino self-interaction, where all the flavors of the neutrino interact with each other with equal strength, and how much it addresses the Hubble tension. Then I'll tell you briefly about the existing laboratory experimental bounds on this kind of scenario and how much it constrains the relevant parameter space, which in turn motivates us to look for flavor specific neutrino self-interaction, and which I'll come at later, and I'll explain what are the new things, how this flavor specific scenario is different from the flavor universal neutrino self-interaction. So for neutrino self-interaction in the context of cosmology, usually it is assumed that the neutrinos interact with each other with a heavy mediator. This interaction is mediated by some heavy particle, a scalar or a vector, with a mass m phi and with a coupling this small g phi. Now, as long as the temperature of the universe is lower than this mass scale, the interaction between two neutrinos can be effectively written as a 4-Fermi interaction, which is shown here. And you can define a effective Fermi constant, which is called G effective, in a similar manner as we do in case of standard model weak interaction, where we have a G Fermi. And the cross section of this process, the scattering process, will be proportional to G effective square. Now, for the values of these couplings, which will be relevant for us, we'll see later that these G effective coupling that we'll use is typically 1 billion times stronger than the Fermi constant GF, which we have in the standard model. This number might look a very large number, but we also have to remember that this G effective represents a weak interaction in the standard model, and it is a really weak, literally a very weak interaction. So this is not something unusual, or it's not a very strong interaction in any way, in any sense. So here's here I'm showing the time evolution of this kind of interaction rate as a function of redshift. The interaction rate has been normalized by the Hubble expansion rate. So when these curves go below the line 1, the interaction basically decouples. So here in the left, you see this yellow dot dash line, which is for G effective equal to G Fermi. So this is the standard, this is the neutrino interaction in the standard model. which involves only the weak interaction, and you can see it freezes out at a much earlier time. But these two blue lines are the interaction rates which we will consider in this work, and you can see that they're because they are much stronger than the Fermi constant, they decouple at very late time. For example, this particular case here, this coupling decoupled just prior to the matter radiation equality. Often it is said that the not just neutrino self-interaction, but it combined with the ineffective. If you combine these two things together, you can solve the Hubble tension in a better way. Why is that? To understand, I'll tell you. We have to understand that we have to first understand what these two things does individually to the CMB matter CMB anisotropy power spectrum. So here I'm plotting three curves of the TT angular power spectrum. The black dashed is for the N effective equals to 3.046, which is the standard cosmology with 3 active states of neutrino and no self-interaction. The red curve is for 3 neutrinos, but with self-interaction with this particular value of the coupling. And this green dashed line is for 4 active states, active neutrino states, all having the same temperature, but without any self-interaction. So the first difference between this red and the green curves you see in this high L region is that the red curve always lies above the black dashed curve and the green line lies below the black curve. So that's a for self-interacting neutrino, there is a boost in the power at high L, whereas for ineffective, there is suppression of power. Why is this? Because if you just increase ineffective without introducing any self-interaction, you are basically adding more relativistic species into the system. And as the free stream, they erase out structure at smaller scales, which means high L. And that gives you a suppression in the power. Whereas for self-interacting neutrino, you are stopping the neutrinos from free streaming. So you're basically inhibiting their power to erase out structure at small scale. So that's why you are, in other way, you are boosting the growth of perturbations at the small scales, and you see this boost here. The other very, very crucial difference between these two scenarios are the phase shift of this power spectrum, which is not very clearly visible here, but it is there actually. Also, in this case, there is these two scenarios, they act completely in the opposite direction. For self-interacting neutrino, the phase shift is towards larger L, so it shifts the whole spectrum towards large L or high L. And for ineffective, the phase shift is towards small L. So you see, in both these modifications, these two scenarios act in the completely opposite directions. So that's how you get you can increase Hubble, but at the same time you can negate their changes in the power spectrum and get a decent fit of to the data. Now, because I'll focus mostly on the self-interacting neutrino, I'll tell you how we get this phase shift in the CMB power spectrum. Now, here I'm writing the positions of the individual peaks in the CMB power spectrum in the L space. So M pi is the particular peak, first, second, third, etc. Phi here is the phase shift due to the neutrino self-interaction. dA is the distance to the last scattering surface from us, and RS is the radius of the sound horizon at the time of recombination. So this ratio here is basically inverse of the angular size of the sound horizon on the CMB map. So now you clearly see that when you increase phi, you are basically shifting the power spectrum towards larger L. So that this phase shift increases L. Now you have to keep the spectrum at the same position because your data is fixed. So for that you have to increase this ratio, which is called theta star, which is the inverse of this dA over RS. You need to increase this ratio to keep the spectrum fixed at its at the same position. Now, how do you increase theta star? You can increase theta star by, let's say, you can increase RS star or you can decrease dA star. Now, one way to do this is by changing the Hubble constant H0, which appears in both dA star and RS star in the denominator. Now, if you increase H0, you are basically decreasing dA star and RS star, but because dA star is an integration over the redshift at late time, see from it goes from 0 to Z star. So the change in dA star is greater than the change in RS star for an equal amount of change in H0. So the change in dA star is dominates over the change in RS star, and that's how you increase theta star. So the final upshot is that you use a larger H0. That's how your dA star. That's how your dA star decreases and your theta star increases, and you get a good fit to the CMB data. So this is a basic mechanism of getting a higher value of Hubble by using neutrino self-interaction. And this is a previous result from Kreisch et al. From the year 2019 of flavor universal neutrino self-interaction structure, where all the three states or three or more number of neutrino states, they interact with the same coupling strength. So the most interesting result here is if you look at the posterior of this coupling G effective with the Hubble. So you see there appears two distinct modes, one at the stronger, at the higher values of GF, one with the smaller values of GF. This will be called as SI mode, which stands for strongly interacting, and this mode will be called as MI mode, stands for moderately interacting. So you see that there is a slight positive correlation of G effective with Hubble. This SI mode corresponds to a slightly larger value of Hubble, but we also have to keep in mind that in this paper, they actually varied the ineffective parameter also. So here the best fit ineffective is not 3, it's much larger than 3, around 3.2 or something, 2 or 3 for this blue contour. And you get a larger value of Hubble. So to be specific, if you take this data set, CMB temperature, lensing, and BO data, you get a best fit ineffective of 3.8 and a G effective value of 10 to the minus 1.41. And with these values, you get a Hubble of 71.1. Now, you can ask how we are getting these two distinct regions in the parameter space of G effective. To understand that, we have to go back to the CMB power spectrum again. And I want to remind you that in case of neutrino self-interactions, not all the CMB modes are affected because of the neutrino interactions. Only those modes which enter the Hubble horizon before the neutrino decoupling, they get affected by these new interactions. All the other modes which enter the Hubble horizon later than the than the neutrino decoupling, they are not affected at all. So what is happening here for this SI mode is that the neutrino decoupling is happening at much later time, which I have shown in the first slide, is that it happens just prior to the matter radiation equality. So in that case, essentially all the modes to which the Planck's experiment is sensitive to, all these modes are virtually affected because of that. And you can then use the degeneracy with the other parameters like H naught, the amplitude of the primordial fluctuations AS, the spectral index NS, the optical depth to the reionization tau, and matter density. You can use, in that case, you can use all these other parameters, the degeneracy of G effective with all these other parameters to get again adjust them accordingly so that you can get a better fit to the data. So you have room for that, which is shown here. As you can, if you start with this red curve, where we have just used the this large value of G effective, then we keep adding all other parameters, and finally for this green curve, we can see we get a very good fit to the data. But for the moderately interacting mode, the decoupling happens at much earlier time, so that only very small modes are affected. And the Planck experiment was not sensitive to all those small modes. So that's why you can again get a good fit to the CMB data. But in the middle, the decoupling is happening at such a time so that only some modes in this range are affected, but others are not. So there is a partial modification in the CMB spectrum. But but then it becomes tricky, because you cannot then use this other parameters H naught, AS, NS, tau, or whatever to use their degeneracy with G effective, because these are the global parameters, or in a sense that they change the whole power spectrum globally. So so we cannot play this game here, and there is a less the fit is not all that good in the middle. So you get two separate regions in the G effective. And similar thing happens for the polarization and cross temperature polarization, cross correlation also. Now for the laboratory constraints. So you can assume that this new interaction arises from because of the interaction of these neutrinos with some heavy scalar particle phi. And then you can ask, what are the new BSM signatures that you can look for in, let's say, cosmology, in other parts of cosmology, or in your laboratory experiments because of this new interaction. So for example, because this mediator is of the order, the mass of this mediator is of the order MeV or even less, it can affect your BBN result if it gets thermalized with the visible sector. So you get a bound from BBN, and also because of this new interaction, you will get new decay channels for mesons, for tau, and there will also be extra processes for 2 neutrino double beta decay. So all of this will constrain your parameter space. And in this paper, they have very nicely compiled all of these constraints. And in the left plot, you see that the SI mode, the parameter space for the SI mode and the MI mode are mostly ruled out by all these bounds. Whereas if you allow only, for example, the tau neutrino to couple to the scalar, new scalar, you can see that much of the MI mode parameter space is open again, and a little bit of the SI mode is still allowed. So you see that there is a strong bound from the laboratory experiments on this universal structure of coupling. So that leads us to see what happens for flavor specific case. So for example, you can ask, instead of all these three neutrinos having the same strength of interaction, what if only two of them had the strong interaction, or only one had the strong interaction, whereas the other states have no interaction at all? So we'll call these three scenarios as 3C plus 0F, 2C plus 1F, and 1C plus 2F. So this nomenclature is quite obvious. You can see this C stand for the coupled states and F for the free streaming states. But of course, in general, you can have all sorts of combinations in the coupling matrix here. And but to keep things simple, we have assumed that the coupling matrix is diagonal, so there is no off-diagonal coupling. And we will also consider only massless neutrinos, because if we include mass, there could be some additional cross couplings between different states. Now, with this simple setup, let's see what happens for different 3C, 2C, and 1C scenarios. Here, we are again I'm again showing the CMB, TT, and EE power spectrum. So you see the compared to the lambda CDM spectrum, as you decrease the number of interacting states, you are decreasing the amount of changes in your CMB power spectrum. So the change is maximum for 3C, and it is minimum for 1C, which is obvious because with less number of neutrinos self-interacting, the change in the CMB spectrum is proportional to the amount of self-interaction. So if we decrease the number of states, you decrease the amount of self-interaction. Same thing happens for polarization. And because of that, we see a huge boost in the in this SI mode for this new G effective. So here again, this green is for the 1C, blue is for 2C, and the red is for 3C. So this strongly interacting mode was almost invisible for this for when all the neutrinos had self-interaction. But you see there is a huge boost in this the significance of this strongly interacting mode for 1C. And we also see that there is a slight, as expected, there is a slight positive correlation with the Hubble parameter here, and there is strong negative correlation with AS and NS. These are the 1D posteriors for a few relevant parameters. Again, you see that the significance of this strongly interacting mode is highly boosted as you decrease the number of interacting states here. Another thing to note here is that there is a little bit of shift in the strongly interacting mode when you add the CMB polarization data. So you see the red posterior is only for the TT, full TT data, and only low L polarization data. But when you add the high L polarization data, the posterior shift towards smaller G effective. It has to do with the relative error bars in the polarization data, which are smaller at small L and bigger at high L. So it's more sensitive to the changes in the small L, and that's why it shifts the whole posterior towards a smaller coupling. Now let's see what happens to the Hubble constant here. As I said before, there is so these are the 1 sigma, 2 sigma, and 3 sigma contours for 3 different cases. And you can see that there is clearly a positive correlation of G effective with Hubble. If you increase G effective, if you are sitting on this strongly interacting mode, you can get a moderately large value of Hubble. However, you can also see that as you decrease the number of interacting states, the central value of Hubble is also decreasing. So you see the red contour is high up here. So the blue contour is slightly below the red contour, and the green is even below down here. And this is also explained, it can be explained very easily, because as you are decreasing the number of interacting states, you are decreasing the change in the CMB spectrum. And as a result, your change in the Hubble is also not that much. So although the significance of this SI mode increases as you decrease the number of states, but the resulting value of Hubble also decreases. Here I'm just quoting one value for the data set of TT, TE, EE, and lensing. So we get for 69.5 here. Now, depending on the what data set, low redshift Hubble data set that you consider, if you consider the TRGB measurement, then you see that this value is totally compatible with the TRGB measurement. But if you consider the Rees et al. Data, then you see that their value is 73.2, which is about like 2.5 or 2.6 sigma away from this value. So, so the final thing is that you can increase the value of Hubble with this mechanism, but you cannot still completely do away with the tension with the Rees et al. Data, but it certainly is compatible with the TRGB measurement data. Now, with this, I'll conclude my talk. I have talked about neutrino self-interaction and the how it explains with larger ineffective, how it addresses the Hubble tension. But at the same time, this large G effective value is incompatible with several different laboratory and cosmology data, and that motivates us to look for flavor specific neutrino self-interaction. And with this flavor specific interaction structure, we see that the modification in the CMB power spectrum is less, and as a result, you have more room to use the degeneracy with other parameters, so that you can get a good fit to the CMB data and still can explain a larger value of have a larger value of H naught. But this is not all. We still have more work to do with. This was only with massless neutrinos. But if you include massive neutrinos, there will be some off-diagonal couplings, and we need to look at that, and there might be still some new effects in that direction. I'll stop here, and thank you.